Hi, welcome to the dynamics tutorials. So in this problem we're still doing equations of motion, but now with polar coordinates. So we have a slotted path, and I just drew the path, I didn't draw the actual slot. But this slotted path in purple, this particle in blue is traveling along that path, and then we have this slotted arm that's swinging around here with some given angular velocity, theta dot, and some given angular angular acceleration, theta double dot. The path is the spiral path, so it's described by this equation. R is equal to 2 times theta, and R is in meters when theta is in radians. Motion is in the horizontal plane, so we don't have to include the weight due to gravity in our free body diagram. And then the mass of the particle is 5 kilograms, and then this is part of the problem statement. So at this angle of 3 pi over 4 radians, so this angle here along the x-axis would be an angle of 0. Then theta dot is 2 radians per second, and theta double dot, the angular acceleration, is 1 radian per second squared. We want to find the force exerted on the particle by the arm, and also the normal force exerted on the particle by the slotted path, the purple path. So if we draw a free body diagram, the first thing is to kind of figure out our coordinate system, and sometimes it's easier to do if we start by actually looking at the particle. So in this case, the tangential direction is going to go in just the direction of the path as the particle moves. The normal direction would go opposite the tangential direction in towards the curvature of the path. So those are our t and n axes, and I just copied those down onto the particle. Then we'll have an r axis, and r is defined as the continuation of the r vector. So the r vector starting at the origin, and then the axis is continuing that out, so that would be our r. And then perpendicular to r would be our theta direction. And remember that theta goes perpendicular to r, but it also goes in the direction of increasing angle. So those are our radial, r, and transverse theta axes. So that's all translated down onto this particle, and then now we can add our forces. So we'll have a normal force. The normal force has to be normal to the path, and so the n direction is giving you the direction that the normal force is acting. Now this is a slotted path, so we could draw the normal going in this direction, or we could draw it going in this direction. Either one would be okay, because it could have a normal force from either wall on either side of the slot. The same thing for the slotted arm. The force could be on either side, but it's going to be in the direction of increasing theta, or in the direction of, in the opposite direction of increasing theta, because that's where the arm contacts the particle. It's in the r axis, and so the normal force goes perpendicular to that. That would be in the theta direction. So I just drew it in the positive theta direction and called it FA, force, and then A for arm. So I've also put the x and y coordinates. We're not really having to use those on this problem, but just as for reference. But we do need to use both the normal and tangential and the radial and transverse coordinates, or polar coordinates, on this one, because we have forces that are going using each of those two coordinate systems. So our first step with these is to relate the two coordinates together, and we can do this with this angle phi. This angle phi is defined as the inverse tangent of r divided by the derivative of the r distance over theta, so dr d theta. So we can get dr d theta as the derivative with respect to theta of our path. So that'll give us just 2, because it's how r changes with respect to theta, and theta is in radians. So theta is basically unitless. then the dr d theta will have units of meters. And then we can get our r distance just by plugging in 2 times the angle, and we'll get the 4.712 meters. Now we can plug it all in down here and then take our inverse tangent, and we get 67.0 degrees. That's a positive angle because both of these were positive, and so positive angles have the sense of starting from the radial axis and then going towards the tangential axis in a counterclockwise direction. So it means the tangentials over here, we already kind of knew that based on just inspection though. And then from here, the next step is really just the same thing that you did with kinematics with polar coordinates, is to fill in this table. So you want r, r dot, r double dot, theta, theta dot, and theta double dot. Now these quantities with theta were given in the problem statement, so I just copied those down here. R dot would just be the first derivative of 2 theta with respect to time, so you get 2 theta dot. And then R double dot would be the second derivative, so it'd be 2 theta double dot. And then we plug in these values and we get those values there. The next step, again, just in the same way that you did with the kinematics problems, is you can calculate your radial component of your acceleration and the transverse component of your acceleration from the formulas in the text. And then finally we can do our sum of forces. So we're going to do sum of forces in R. And so in R, FA only goes in the theta direction, so FA has no R component. The only force that has an R component is NA. If T is moved off of R by this distance here, then theta will be also that angle from N. So we can get the NA sine of 67.0 degrees is equal to 5 kilograms times the radial component of the acceleration. We can solve for that and get NA is equal to negative 91.5 newtons. And then we can do the sum of forces in the theta direction and get that that's m times a theta. Now we have both the FA force, which entirely goes in the theta direction, so here, and then we have the other component of the NA, but we've already solved for NA. And then we can solve that equation for FA. Thanks for watching.